eccentric orbit change climate? That's right. So cold weather occurs on this half of the orbit, right, when you're slightly farther away. Instead of some kind of complicated physics term, insolation. INSOLATION, the amount of sunlight that gets into the planet. Insolation. Not insulation, the big stuff you throw in the attic. Low insolation. Actually, I should probably draw it more like this if I want to equalize the semi-major axis. It's going to be shorter. This would be a region of high insolation. Well, I got high insolation, I got low insolation. The amount of average insolation, if I average over the path, should be the same. But remember, we're not taking into account time. Kepler's second law says you will speed through this section of your orbit much faster, faster, depending on how eccentric you are, compared to this section. So they may spatially average, but they do not temporally average out. Your planet gets less insolation at this eccentricity than it does at the second eccentricity. And it's enough to make a difference, especially when it builds up over multiple years. So interesting, I never thought about that. The Earth her orbit is not circular about the sun, and before it changes, it wobbles a little bit. Now, how often does it wobble? Well, this occurs in a fairly regular cycle. So if you think it's going to change next year, have no fear. The major cycle is 413,000 years. And there are some minor cycles in between. Yes. That's right. And we have to be careful about using winter and summer because it's going to be summer here in the northern hemisphere, but it's going to be winter. But really, insolation throughout the year is lower. Average insolation over time is slightly lower. I know what you mean. That's the way to think about it. Interesting. Okay. And as you can see right now, our current eccentricity, we're actually a little bit closer to this right now. I have recorded into my notes that last year we were at 0.012. I'm guessing we're probably at the same eccentricity this year. Almost circular. Colder times ahead. Maybe, I don't know. Not anytime soon. Now, the second orbital-forcing element, precession. Okay, I got the sun. Here's the orbital plane coming out of the void that the Earth makes with the sun. Here in the northern hemisphere, when our rotational axis points away, we get summer. And on the other side of the orbit, we get, this side we get summer, this side we get winter, the south gets summer, and the south gets winter on this side. And for the most part, we maintain this because, generally speaking, when you have a rotating object, the angular momentum is conserved in a particular direction, and you stay oriented like a gyroscope over time in your orbit. However, anybody that's familiar with the top of the table knows that for the most part, short periods of time, that's true. But over time, that axis will actually precess. And the Earth is no different. We actually have precession on the Earth. And what that means is that over many, many times, this will eventually flip over many years. The actual cycle for this happening is 26,000 years. So right now, perihelion coincides with a northern hemisphere winter, and aphelion corresponds with a southern hemisphere winter. So based on that, who do you think experiences the most extreme seasonal swings? The north or the south? Oh, the south, right? The south is the farthest away from the sun during its winter, and the north is actually the closest during its winter. So you expect those to be different. In the south, it's going to be closest when it's summertime. And generally, we've observed that. In the southern hemisphere, the seasons are slightly more varied than they are in the northern hemisphere. Now, at the current time, the planet is not particularly eccentric in its orbit. So these are two phenomena that can reinforce one another. You don't see much of a change when E is 0.005, but you may see a more significant change when E is at its maximum of 0.058. Now the question is, does this affect insolation of the planet? Well, the North experiences milder seasonal changes now, and the South experiences more significant changes later, and vice versa. So it's just putting the shoe on the other foot, right? However, it does have a significant effect on climate. Why? What's different between the north and the south hemisphere on the Earth? Would you say? Yeah, the land mass. Since we went to Asia, there's a lot more land mass up in the northern hemisphere. More trees, less algae, and you get these seasonal swings can influence the biomass significantly. Hopefully, you don't have to worry. The rivers in the northern hemisphere can relax in our extremely mild winters and our extremely temperate summers for the next 13,000 years. Okay. Number 3, obliquity. Obliquity. This is also related to the Earth's rotational axis. And this is kind of a peculiar phenomenon. But the Earth's axis, you've always learned it to be 23 degrees roughly from the sun, from the solar equator, or the plane, the orbital plane that the Earth makes with the sun, what's called. The current obliquity is 23.44 degrees. Almost right down in the middle. Maybe a little closer to the end. But certainly not the most extreme that the planet can get. And this is a problem too. First of all, it doesn't affect net insolation, but the higher the obliquity, the more extreme the summer and winter become. The harder it is to grow things. That also influences the biomass significantly on the planet. So who knows what that does? And there's one final change, and I don't believe we have a good estimate for the cycle that this happens, but we know that it happens and it will have an influence. The sun, this is inclination of the Earth orbit. The sun has sort of a median plane over which all of the planets revolve around it. And the Earth has a slight amount of inclination with respect to that plane. What do we say, like 7%, 7 degrees roughly? So it's a little bit off. And it'll go around and around in this fashion. But it also wobbles. It will tilt up and down and up and down over thousands, tens of thousands of years at least. Now, why would that change anything? So I have to do something with a question. Let's go back to a question that somebody brought up earlier. I think it's really good. That is, does everything lie on a plane in the solar system? Just what answer is yes, most things do, because we form these accretion disks that turn into planets and all. However, not everything belongs, not all the mass belongs to a planet. There's a lot of debris. Most of it just dust size that exists all along here. And so, for example, we notice that twice a year, on opposite ends of the year, when we pass through the accretion disk, the median plane where there is more stuff, we see a slight increase in meteor activity. Dust and particles and little rocks and fragments that fall into the Earth. And so, scientists speculate that when the plane lines up with this plane, this mass, that will result in slightly less insolation, because it just gets a little dusty. And you don't notice it from Earth. It's probably not observable on a day-to-day basis, but it's slightly lower insolation, which will build up over time and change the climate until the Earth comes out of that inclination of zero. So I think it's interesting because it kind of teaches you to think in 3 dimensions and reinforces a lot of the orbital concepts and irregularities that we learn in the class. And, there's always a lot of talk about climate change. There's a very good, healthy discussion to be had about, how do man-made things influence the climate, what should we do to change or alter behavior. The one thing you must never do, though, is say something that one of my colleagues said one time, and I was out to lunch with them. He said, it's clear that we are violating some sort of equilibrium in the planet with our activities. There's never been an equilibrium in the planet. It's been chaos since the beginning. Deal with it. So, any questions about irregularities or orbital forcing? You'll be happy to know that the next ice age isn't until 50,000 years. So we're safe. We're safe. Yeah. Slingshot around Earth. I think it will get more here. The short answer to the question, to repeat back in case you didn't hear it on the video or in the back, was when you're inserting yourself or slingshotting with Jupiter, you have to consider the mass of the moons around Jupiter in your calculation. And as short as it might, yes, it's not that hard to do, so I'm sure that the solvers model those anyway. It probably doesn't make that much difference, though, because Jupiter does have a few very large moons, but still as a fraction of the total mass of the planetary system, it's much smaller than the percentage mass of, say, the Earth's moon and the Earth. The Earth is actually very unique as a planet because it's almost considered a dual planetary system because its satellite is one of the biggest satellites in the solar system. And, it's almost where you can't even, you have to model the centroid of the two, so many hundreds of kilometers away from the center of the Earth. So really it's almost like a dual planetary system that orbits around itself as it progresses around the sun. Now when you're dealing with the Earth, and you can approximate the satellites around the Earth because you tend to be a bit farther from the moon and it's not as nearly as massive as the Earth. In that scenario, geostationary Earth orbit is less. You don't really have to worry about it other than to correct your orbit every once in a while. When you get out to the moon orbit, if you want to orbit something that's really far out, higher Earth orbit, then you start getting into some weird orbital mechanics. There are these stable points, for example, called Lagrangian points around the moon, where if you insert a spacecraft in there, it'll just kind of hover in moon synchronous orbit. It's just kind of in between the Earth and the moon, or you can spiral it around the moon in a semi-stable orbit as it tracks around the Earth. Just a lot of really interesting orbital mechanics that you can get into, but obviously a very specialized application. Okay, how are we doing on time? Oh, 1 minute left. Any other questions before we leave? Yes. How do you go through the asteroid belt? It's true that there's a lot of junk in the asteroid belt, but as far as navigating through it, you pretty much play the odds. The density of the belt is extremely low. You don't have a huge number of running into something. It's not like Star Wars where it's like, like this or like any other space. That's all more dramatic to portray an asteroid in that fashion. The sad matter is it's slightly more dense than all the other junk out there. There probably are giant space worms living on there either. But that's just a guess. Don't quote me on that. Series. Earth station look angles. And this lecture is really about answering one question that is near and dear to the heart of any electrical engineer working in the satellite field. And that is, if I am an observer where I'm in the satellite, what the answer? At what time of day, and at what point is the satellite in orbit, and how do I actually work in the instrument to it to actually get the signal? Many of these space links, as we've seen in the parts of this class, satellite links are unique among the links that we use in day-to-day life because they have to overcome thousands of kilometers of path loss in order to get to your local station or your Earth station from the surface of the Earth. So how do we overcome that? Well, one of the ways that we're going to learn when we get into antennas and propagation is you got to make a really big dish. The really big dish has a lot of directivity to focus power and receive efficiently from a particular direction, but also has a potential bit beam, which is good because when you a particular satellite up in the sky is pointed, you can get that satellite with a lot of beam and you'll exclude everything else. Everything else will have significant amount of attenuation, even other satellites that are using the exact same bands. So now you reduce frequency in space when you're not going to have the luxury of the cellular network having building in trees and blocking signals and filtering out from other regions of the cityscape. So we use directional dishes quite a lot in satellite communications. The downside is that you have to point because they only have high gain for maybe plus or minus a few degrees of beamwidth in those locations. And so you got to figure out where to put it. You have to figure out where to hammer that direct TV dish into the ground and what angle to put it at in order to get this TV signal. That's the simplest application for that. Okay. So that's the question that we're answering today. And let's answer it by starting off with the typical geometry of the problem. And this is going to introduce some really important jargon that we're going to use for the rest of the class. Here's the Earth. Here's the center. So the point where you're observing something, radiation from the satellite, we're called it the Earth. Station often abbreviating it as ES in this class. And then you, of course, have the satellite in space itself. And if you draw a line from the center of the Earth to where the satellite is, the place where that intersects the Earth has a special name as well. That's called the satellite subpoint. We'll abbreviate that SSP. And if you were standing on the satellite subpoint, The satellite would essentially be directly overhead. We call directly overhead zenith, this direction. And then looking backwards down to Earth, we call this nadir. And the key parameters for figuring out look angles are basically, first of all, the fixed constant that is the radius of the Earth. So radius of the satellite, that is the distance from the center of the Earth to the satellite, space constant. And, of course, the longitudes and latitudes of both the Earth station and the satellite submarine. Now, as a quick refresher, you probably all know this, but I'll put it on the board so you have it in your notes. We use longitudes and latitudes to denote satellite subpoints and Earth stations. We're going to give numerical values to these. Longitude 0 degrees is, of course, where? Greenwich, England, which is kind of line with one. But I think Greenwich is the official demarcation. Exactly. If you have positive values, you are moving east of Greenwich. And if you have negative values, you're moving west of Greenwich. Now, keep in mind, because there's a too high kind of a repetition period to describing longitudes, you can get multiple longitudes for the same point. You could say, oh, this point is at 270 degrees longitude. I mean, you start at Greenwich, you move 270 degrees east. Well, some people prefer to use negative 90 to denote that. That's negative 90 degrees. And some people, instead of using positives or negatives, they'll use east or west. They'll say 90 degrees west as opposed to 270 degrees east. It all comes out in the wash. Just recognize the different conventions out there. You see a west next to the degree marker for longitude. Engineering building, which is not the building where this class is, but the building where some of these